Our next speaker of the day will present how he and his team are working on developing molecular materials that capture, store, and release both solar and ambient heat without creating any emissions. I present Professor Kasper Moth-Poulsen. Kasper, please take the spotlight.
Brilliant. So thank you very much for your kind introduction and the invitation to come here today. So my name is Kasper. I'm a professor at Chalmers University of Technology and also at the Polytechnic University of Catalonia in Barcelona. And I'm going to tell you about a project that actually started for me about 15 years ago when I was doing a postdoc in Berkeley in California, where we started to work with a new class of materials that can capture solar energy and release the stored energy as a heat on demand. So, needless to say, in this forum, we have a very polluted world. And for example, in Sweden, we are losing about 7,600 people each year too early due to air pollution. And in Europe, it's about 800,000 people every year. So on average in Europe, we lose 2 years of our lives due to air pollution. This is more than COVID, but we don't close our homes because of that. Uh, but luckily, we are working on new technologies that are uh, uh, creating less pollution, for example, solar and wind. But the and this is being introduced at a rapid pace. But we also need to be able to store the energy for when the sun doesn't shine or the wind doesn't blow. Um, Moreover, there's another problem, and that is that uh, electric power is only 25% of the end use of energy in EU. The other 25% is the transportation, and then we have 50% of the end use of energy in Europe is heat. So this is heat is for households, heating water, heating our homes, and for industry. Um, and most of this heat is coming today from fossil fuels. So in my group, we are trying to develop new types of energy systems that can deliver heat on demand without creating any emissions. So our goal is to develop new emission-free ways to control temperature in general, and in the future, both heating and cooling. So how can we think of that? So the type of energy system we're working with we have called molecular solar thermal energy storage systems, or MOST. It works like this, that we have a parent molecule, we shine light on it, and then it undergoing a photoconversion. This is the same type of conversion that we have in our eyes. The vision system in our eyes are also photoconversion. Every time a photon hits your eye, you have a photoconversion that is transmitting a signal to the brain. Here we have a photoconversion that is changing the shape of the molecule. And this photoisomer that we are creating can then store the energy for extended periods of time. And very importantly, this molecule is not heated in the process. It's only when we trigger the heat release by the use of a catalyst we generate the heat, and then we recover the parent molecule. So this is a closed cycle where the only input is light and the only output is heat. And we don't have any insulation materials because it's a chemical transformation. It's not a physical transformation like in phase change materials. So this has high potential, but they also have the problem that someone needs to develop the material. And that has been our mission for the last 10, 15 years. So uh, several systems are being developed around the world today. Uh, since we started in California 15 years ago, a lot of research groups, both in US, Europe, and Asia, has come to try to develop systems like that. And the system we're working on is called Norbornadiene, and it is uh, based on well, the name comes from a natural product that looks a little bit like this. And when you photoconvert that, you store up to 1 megajoule per kilogram. That is energy equivalent of 280 kilowatt hours per kilogram. But of course, here we are not producing electricity, we are producing heat on demand. So when we back convert the quadricyclane to the norbornadiene, we generate this heat release. The problem is that the system as we have it here, we cannot photoconverted really well. So we need to engineer these materials, and there's been going a lot of man-years into the chemistry of these. And I will not go much into detail on how we have developed them, but just say that this is a core of our work has been to actually improve the performance of these systems. But in my group, we're not only making the molecules, we are also trying to develop demonstrator devices that in a simple way try to show how they can be used in the future in different energy applications. So we start out from the left, we have the ideas, then we make the material, we evaluate it, and then we test it. And today in this talk, I'm going to focus mostly on the testing end to illustrate what this technology could become in the future. So after 10 years of research, we had made this molecule that was an improved version of the previous ones that had a fairly high energy density, but notably could also be converted by sunlight, and it could be dissolved in a solvent. And with this, we wanted to demonstrate that we could heat something. So we have been working for several years, and it's a little bit ironic, but actually just getting to the place where we can actually start to release the heat and actually feel it was an achievement back then. So by combining this molecule in large amount together with a solvent and a catalyst, we could start to work on the actual heat release device. So back in 2019, we built this device that contained a vacuum system to reduce heat losses. It had an inlet and an outlet, and in the middle there was a catalyst. And on a special day in Gothenburg, Sweden, at Chalmers, we saw for the first time this heat release. And the first experiment led to a heat release of about 50 degrees, a temperature gradient. And we have calculated that the maximal theoretical gradient we should get would be about 65 centigrade. So it was done at room temperature, so around a little bit less than 90 degrees operation temperature. So by refining this work, we actually got all the way up to 63 degrees, and this was just 1 degree lower than the theoretical prediction. So we're very happy about that. And even American broadcasting company CNN flew to Gothenburg to make a small TV program about this achievement. Um, we have continued to work on the systems and try to see if we can make gradually more realistic demonstration devices. I must admit that it's still early stage development, but we're pushing ourselves towards closer and closer towards public applications. So in another piece of work, we demonstrated that you can continue to operate the system using catalysis for the heat release, solar light, simulated light for the energy storage. And in this case, we did, I think it was 50 or 60 cycles, so 120 chemical reactions without any significant degradation of the system. And moreover, we tried to combine it with a thermoelectric generator system so that we could produce electricity on demand. And although the efficiency was very low, this is a demonstration of a very different energy system that, I mean, the equivalent would maybe be a traditional photovoltaic and a battery. But there you have all the materials constraints of batteries and photovoltaics. So here we have a molecular solar thermal system made of carbon and hydrogen together with a thermoelectric generator. So both the energy capture, solar energy capture and energy storage is in a entirely carbon-based material. And then you have some materials in a thermoelectric generator that then produces electricity on demand. And this work was highlighted by General Electric company in the US as one of the 5 coolest things on Earth this week. So efficiency is still low, so we are continuing to push this technology and try to see if we can make it more realistic. In a somewhat larger European project together with universities in Sweden, Spain, and Denmark, and research institutes in Germany and companies in UK, we have tried to build a somewhat larger scale device for this technology in order to improve the efficiency, but also try to get metrics that we can use for further development in the future. So here we built, I would say, the world's largest device so far. It's about half a square meter, and it's been tested on the roof of our building here in Catalonia in Barcelona. We can see the device here on the right-hand side. It contains two different components. The top part is the most solar collector that stores the solar energy as a chemical energy. And the lower part is a traditional solar thermal collector system. So the two energy streams is split up, and the molecular system is stored in a storage tank, and the thermal system can also be stored in an insulated storage tank. And then the two streams are going into a heat exchanger where the most system can be used to upgrade the heat of the thermal system to reach higher temperatures, or to regulate the temperature of the thermal system so that you get a stable temperature output depending on application. And right now we are doing a test, and although this maybe looks small compared to some of the other demonstrators you have seen, this is by a factor of 1,000 larger than anyone has built before for a molecular solar thermal system. And this demonstrator was recently featured in Catalan TV here in Spain. If we continue, this is the team behind it, and we have up to 80% solar collector efficiency. So we convert up to 80% of the incoming sunlight in the combined system. So if we go take a little bit closer look to the performance of photovoltaics. So photovoltaics are really, I would say, the most impressive deployment of renewable technology. And the majority of the photovoltaics that we have today are made using silicon. And this silicon-based system, they work like a little bit like this, that you have first a charge separation induced by light, and then the charges travel to the two electrodes, and it can run and create work in the power device. But there are some challenges with this type of technology. One of them is that longer wavelengths, lower energy photons will not be absorbed by the bandgap. Another one is that if you have higher energy photons for the blue and the green, you actually lose most of the energy due to thermalization because you can only use the energy that is in the bandgap. And finally, you have recombination losses that simply this charge separated states, they recombine and go back to the starting point without generating the workload that you want them to do. So the solar cells are most efficient at the onset at 1100 nanometers. There they are operating, I think, 80-90% efficiency. But at 400 nanometer, there's 80% thermalization losses, meaning that they operate by less than 20% or even less than that. So also the non-radiative decay rate increase with temperature. So the warmer the solar cell gets, the lower the performance it has. And this is why in Europe, the best place for photovoltaics is in Germany and the Netherlands. They have the best combination of low temperature and high irradiation. Whereas in Spain, where we have much more sunlight, they get too warm and they drop in efficiency, and therefore they're not working to full performance. But we realized then that our MOST system, they actually operate at 30 to 50% energy capture efficiency at 400 nanometer. So they are more efficient than the photovoltaics at these wavelengths. And this maybe could lead to a combination that was creating new opportunities. So if we just look at the first about the performance of a sort of standard, not super well-performing solar cell at 0 degrees, it's operating at 15% efficiency. But if you heat it to 80 centigrade, it drops to 11. So it loses about more than about a third of its energy conversion capability. So our idea was then to put the MOST system on top Most systems reach the sun first and convert some of the energy into stored chemical energy. The remaining photons that will be mostly all colors of the spectrum except for the blue and the ultraviolet will then hit the photovoltaic. Remember that the blue and the ultraviolet are the photons that are thermalizing the most, so we should be able to reduce the heating of the photovoltaic as well as adding a storage component in our system on top. So this is how it looks. It's a quite small device. It's 1 by 1 inch, but you have the liquid flow device on top and the solar cell underneath. And by combining these two, we actually improved the efficiency of the photovoltaic and added about 2.5% of energy storage, which is a current world record in energy storage using molecular solar thermal materials. So it may not sound like much, but compared to other direct conversion of solar energy into chemical energy, this is one of the most efficient processes that are available in the world. What more could we do with this kind of system? So one other idea we have is to try to think about how windows work, because we sit in houses, we build houses to create a comfortable working climate, and during the day our house typically gets very hot. And especially if we have windows facing south, we get a lot of heating into our house. So the black curve here represents the normal scenario, very hot during the day and cold during the night. And the ideal situation would be if we have a stable temperature inside. But the problem is that the windows, we want to have a transparent window so we can look out through it without and there's no technology that sort of can regulate the thermal transmission of these windows. So our idea was to create a system where we store the energy in the window and release it as heat during the nighttime. So here is a picture of our first demonstration device. It's very small again. We have a yellow film that is converted into transparent. And then during the nighttime, it will release the stored energy as heat and be ready for the next circle the day after. So this, with future development, this could be a way to transfer energy from the daily to night cycle automatically inside your home or window. We have worked on it a little bit more, and right now with the materials at hand, this will only be able to transform a few watts from the day to the night. So we need to improve the materials further, and this is something we are currently working on. So here is an example of an outdoor test setup we have built. This is a small miniature house, we can call it, with two windows and two compartments inside. And we're testing it now on our roof here. This is a picture of the compartment. We're measuring the flux through the window and also the temperature in order to see if we can regulate the temperature in one way or the other. That's how it looks here in our place here on the roof of one of our buildings. Just at the last 5 minutes or so, 3 minutes, I just want to highlight something else we have been working on. So I told you that we make the molecules, we evaluate them, we test it. But this cycle is extremely labor intensive. So one thing I heard that from the Swedish consulate that automation is one of the focus points of the collaboration with California. And I would say that automation is certainly starting to enter the chemistry labs, and we're trying to build a self-driving laboratory to be able to develop new materials faster. So this is, maybe you have seen a normal chemistry lab before. This is how our chemistry lab looks. It's completely robotized, computer controlled. All the chemistry is happening inside these tubings and controlled by valves and pumps and hoses, and we have analysis and all that inside. So this is I would say, a possible revolution in how chemistry is done that we are working with in trying to accelerate the workflow for new materials. We are also doing this in a startup company located in Gothenburg, now trying to develop further this type of self-driving lab. This is sort of the chemistry version of the Tesla car, trying to make a laboratory that can operate without human intervention. We are also building using some of these methods to build catalysts. And here we are making some of the best catalysts in the world for CO2 and hydrogen conversion. CO2 is a problem in the atmosphere, but there are big efforts in California, for example, in using electrochemistry to extract CO2 from the atmosphere and produce aircraft fuels. And we believe that we have produced by these automated robotized methods, been able to produce some of the best catalysts available today. And actually, we are exporting a good part of our catalysts to California right now, and of course, looking for more clients for this startup also located in Gothenburg, Sweden. So these are some of the startups we have made from our group in the last 4 or 5 years. Conscience is the first company in Sweden to commercialize the superconducting quantum computer chips and are selling them to the whole world. And Nanoscientifica is making Power-to-X catalyst system, and Autosyn is making automatic self-driving laboratories. So these are some of the sponsors, the European Union, the Wallenberg Foundation, the Swedish King, and others. And with that, I would like to thank you for your attention and be happy to answer any questions related to this presentation. Thank you very much.
Thank you very much, Kasper, for this very good presentation. We have quite a few questions, so I will read them to you.
Yeah.
First question, any prospects of space applications?
I think that's a very good idea. And this is, I mean, basically, we have a technology that is, we're really trying to push this new idea, and with the right type of funding, I'm sure that we could come up with something. I would like to be honest with this. I mean, we are trying to move towards application, and specifically for this energy storage technology is not fully there yet. It's probably at what people will call TRL 3 or 4. But with the continued work and investment, and I hope we can push it towards the real world application. That's certainly our goal.
Okay. Next question. What kind of round trip efficiency are you getting with this storage system? And how much further improvement do you think is possible?
Yes. So right now, we are out of the full solar spectrum, we are storing about 2.5% of the incoming light, and then about 80% of this incoming light is going into heating, and that's just a traditional thermal system. So we have calculated that the maximal you can expect to get is around 10 to 12%, and I hope we will get close to that in the coming years. When we started, we were less than 0.00 something, so we have improved the systems orders of magnitude already, and just in the last 4 years, we have more than doubled the efficiency. So it's something that has been improved and will improve, and right now we are about 2.5%. So I think we're better than photosynthesis and better than direct solar to hydrogen conversion technologies where people have invested orders of magnitude more research efforts than in this. So I think we have a good prospect of improving it much further, simply because it's a relatively small research field. I mean, now when we started, there was one research group in the world. Now there may be 15. So I think there's good room for improvement just simply by having more people working on it for a longer time.
Okay, thank you. And another question, could you please elaborate on the capture of CO2?
Yes, so there's a technology called Power-to-X, or electrocatalytic CO2 conversion. So there exists a number of companies now. I should not, you can Google them, but there exist a number of companies in California, in particular, where they use electricity and to convert CO2 into valuable chemicals and or fuels. And one of the biggest one of them, they try to convert CO2 into aircraft fuels. In this way, they could make airplanes CO2 neutral, because it will sort of substitute the idea of pumping up oil from the underground. You'll simply be able to create oil from air and electricity. And for that, you need a catalyst, and that's what we are doing. We are making the catalyst for that type of technology.
Okay, thank you very much, Kasper. I think that was all questions.